Hello everyone, welcome to Byju's exam prep. So today in the Trigopedia session, I am going to discuss the standing wave ratio in the standing wave pattern for the resistive load. So there is a very small trick for the calculation of the standing wave ratio if the load in the transmission line is resistive in nature. Because as we know that in the transmission line, we can have the complex load as well. Generally in the plane wave propagation, we don't see the complex load or the complex impedance, but in the transmission line we have the capacitive load, inductive load, so definitely we will have the complex load in the transmission line. So there is another part that when the load is resistive, especially given in the question, then how can you quickly calculate the standing wave ratio? So before starting the session, and let me introduce myself. This is Saket Verma, and I'm having more than 13-year experience in the field of GATE and DSC, and my area of expertise are these. So let's discuss the standing wave ratio for the resistive load. Suppose you calculate the standing wave, suppose it is given that standing wave pattern, that is the voltage standing wave pattern at the load end. And in the load end, if you find that the voltage minima is occurring, okay, this is how we draw the voltage standing wave pattern. So we will get the maximum after some distance, and at the load we are getting the minimum. This is the exactly value of voltage which we are getting at the load end, and after traveling towards the source we are getting the voltage maximum, and again we are getting the minus lambda by 2. So generally, how do we calculate the standing wave ratio? So standing wave ratio is nothing but the ratio of maximum to minimum voltage and mod of it. But now if suppose in this type of question you see that the load resistance is less than characteristic impedance, you can write it as a Z0 as well. So if the load resistance is less than characteristic impedance, then you get this type of standing wave pattern, and for this the standing wave ratio can also be calculated as Z0 upon RL. So this is the one example that I am taking. This is the standard form to calculate the voltage standing wave ratio from the standing wave pattern. And if this condition is given, as I said that this load is resistive in nature, and if it is less than the characteristic impedance, you will see this type of standing wave pattern, and you will get the standing wave ratio by Z0 upon ZL. Similarly, if suppose the standing wave pattern is given in this form, okay, suppose the standing wave pattern is given in this form. This is, I am again taking voltage standing wave ratio, and if you find that the voltage maxima is occurring, this is the voltage maxima which occurs first at the load end, and when you move towards the source, that is after lambda by 4 distance, you are getting the voltage minima. Okay, so in this case also you will calculate the standing wave ratio, which is the maximum divided by minimum. This is the one case. And the second case is this type of standing wave pattern you get only if the load resistance is greater than the characteristic impedance. Okay, this is the condition. When this condition is satisfied, then you get the voltage standing wave pattern like this. And in this case, you can also calculate the standing wave pattern by RL upon Z0, because the value of standing wave pattern should always, the value of standing wave ratio should always be greater than 1. So whatever is greater, you should keep that in the numerator, because we want the ratio to be greater than 1. So this is the second way to calculate the standing wave ratio if the standing wave pattern is given in this form, okay, or this condition is given. So there are two ways. If this ratio, this standing wave pattern is given, then you can calculate by this, and if this condition is given, then you can calculate by S is equal to RL upon R. So let's apply this in the question. So this is the example where voltage standing wave pattern is given. As you can see that in this graph, the voltage minima is occurring at the load end. So that means the standing wave ratio, if you calculate that, it is voltage maxima divided by voltage minima, and 4 divided by 1 you will get. That is simple standing wave ratio. But what we want to calculate, we want to calculate the resistive load. So resistive load, and if the characteristic impedance is given as 50. So as you can see that the voltage minima occurs at the load, what condition is satisfied? The question, in the question itself given that the load resistance, the load is resistive in nature, and this load resistance is less than the characteristic impedance. Why? Because the standing wave pattern shows that at the load end we are getting the voltage minima. So if we are getting the voltage minima, that means the load resistance should be less than the characteristic impedance, and the standing wave ratio will be given by Z0 upon RL. And we have already calculated the value of standing wave ratio. So now I can write RL is equal to Z0 upon S, and the characteristic impedance in this question is given as 5 and it is 4. So we are getting the 12.5. So answer will be option number C. Okay. And if in this question, if we continue that the reflection coefficient we want to calculate, then obviously voltage minima is occurring, and we can see that the load resistance RL is less than the characteristic impedance. So from the formula of the reflection coefficient, this is RL minus Z0, divided by RL plus Z0. You can put the value of the RL, that is we have calculated 12.5 minus characteristic impedance 50, 12.5 plus 50, you will get the negative value, which is minus 0.6. So answer is option A. So in this way you can apply this particular trick to solve the question. Thank you for watching this session. Don't forget to subscribe the channel and stay tuned with us for more such type of concepts. Thank you.